16th problem says 2-point charges of 2.6 into 10 to the power minus 19 coulomb and minus 2.6 into 10 to the power minus 19 coulomb are separated from each other by this distance. The dipole is situated in a uniform electric field with this much intensity. Find the work done in rotating the dipole by 180 degrees. So we know the term for potential energy when a dipole is placed in an electric field is the dipole moment dotted with the electric field, that is minus Pe cosine theta, where theta is the angle between the dipole moment and the electric field. So initially the theta was 0 cos 0, that is minus Pe, and finally it becomes 180 degree rotated, that means Pe cosine 180 degrees, that is plus Pe. So the work done is Uf minus Ui, that is 2 Pe, and P is basically Q into the distance d into E. Then you have to plug in the values given. 10 to the power minus 19, d is 1.8 into 10 to the power minus 10 into E is 5 into 10 to the power 5, and if you calculate this you will get option A. 17th problem says which of the following pair is incorrect for some transparent media with respect to air. So as you can see, the medium is same for all the options. The refractive index and the critical angle is different. So we know that sine of critical angle is equal to 1 by the refractive index of the material, or by dividing with sine theta c and multiplying by n, you will get n each 1 by sine theta c. So you plug in these angles here and try to see if the refractive index is matching or not, and you will find out that for these three options this is matching, and for the fourth option, if you plug in the theta c as 29.14, you will not get the refractive index 1.12. So this is the incorrect statement, option D. 18th problem says let the electric field amplitude of an electromagnetic wave is E0 equal to 90 Newton per Coulomb, then that its frequency is 50 megahertz. Find B0, K and lambda. So as we know, B0 is E0 by the speed of light, which is 90 by 3 into 10 to the power minus 8, that is 300 into 10 to the power minus 9 Tesla, that means 300 nano Tesla. So you don't even need to calculate K and lambda, because only one option has B0 is 300 nano Tesla. Okay. The static friction is a self-adjusting force up to its limit dash. Do not put dash without being sure that the maximum value of static friction is coming into play. So basically you need to find out what is the maximum value of static friction and what is the value of static friction in general. So suppose you are placing an object on a rough surface and you are pushing it with a force F, then it will have a frictional force F, and as we know, if you plot the frictional force versus the applied force, we will be able to see that as the applied force increases, the frictional force increases up to a certain point, and then it goes like this, and this maximum point is the maximum static friction, which is mu s, or mu static times the normal force on the system, which is this, and F is always less than equal to mu s n, so the maximum value is mu s n. So option C is correct. The amplitude of a magnetic field part of a harmonic electromagnetic wave in vacuum is V0 is 480 nanotesla. Find the amplitude of the electric field part of the wave. So we know E0 is C into V0. So 3 into 10 to the power 8 into 48. So this is 144 Newton per coulomb. Option B. 21st problem says which of the following is correct expression for cyclotron frequency. So as we know, the force on the charge because of the magnetic field is QBB, and that is equal to mv square by r, the centrifugal force. And from here you can calculate v by r as qb by m, and we know the time period is 2 pi by omega, that is 2 pi r by v. So this is 2 pi m by qb. So frequency is 1 by t, which is qb by 2 pi m. Option D. Now find the charge and the potential difference across C1 of capacitance 1 microfarad for the given circuit. So this capacitor and this capacitor are in parallel combination, and their resultant capacitance is 1 microfarad plus 1 microfarad, that is 2 microfarad. So the equivalent circuit becomes 2, this is 2, and this is also 2. This is 4 volt, this is 2 microfarad, 2 microfarad, 2 microfarad. Since the capacitance are same for the three capacitor, so using symmetry we can say that the potential difference across each of these capacitor is 4 by 3 volts, because the capacitance are same. And so the charge on each of the capacitor would be 4 by 3 into 1 microfarad, that means 4 by 3 microcoulomb. So the voltage is 4 by 3 volts and charge is 4 by 3 microcoulomb. Option D. Double convex lens are to be manufactured from a glass of refractive index 1.55 with both faces of the same radius of curvature. Find the radius of curvature required if the focal length is 30 cm. So from the lens maker equation, you know 1 by f is mu minus 1, 1 by r1 minus 1 by r2. So r1 is positive, r2 is negative for double convex lens. So if r1 is equal to r2 as given in the problem, 1 by f becomes mu minus 1 divided by 2 by r. So radius of curvature is 2 into 0.55 divided into 30. So the answer is 33 centimeters. Okay. Twenty-fourth problem says when a 3 microcoulomb of charge is carried from a point A to point B, the amount of work done by electric field is 75 microjoule. Determine the potential difference. So the work done from for taking the charge from point A to point B is basically the charge times the potential at A minus potential at B, that is Q delta V. Q is 3 into 10 to the power minus 6, and this is delta V, and W is given as 75 into 10 to the power minus 6. So you will get 25 volts for delta V, option B. 25th problem says a magnetron in a microwave oven releases electromagnetic waves with frequency 1980 MHz. Find the magnetic strength necessary for electron to move in circular track with this frequency. So as we know, the frequency is for a cyclotron is QB by 2 pi m. So B is 2 pi nu m divided by q. So this is 2 pi 1980 into 10 to the 6. This is 9.1 into 10 to the power minus 31 divided by 1.6 10 to the power minus 19, and if you calculate, you are going to get option A. Okay. Circular coil of 50 turns and radius 10 cm carrying a current 5 ampere suspended vertically in a uniform horizontal magnetic field of magnitude 1 Tesla. The field line makes an angle of 90 degree with the normal of the coil. So this is your coil, and this is the normal direction, and your magnetic field is the normal direction. It is 90 degree with the normal direction. Is this angle is 90 degree. Now calculate the magnitude of the counter torque that must be applied to prevent the coil from turning. So as you know, the torque for a magnetic dipole when it is placed in a magnetic field B is the magnetic moment cross product with the magnetic field B, that means MB sine theta. Now the magnetic moment is current times the area of your circular coil times the number of turns B, and sine 90, which is 1. Now current is 5 ampere. This is pi into 0.1 meter square into 50 into 1 Tesla, and the answer is 7.85 Newton meter, option B. Calculate the speed of the electromagnetic wave in a medium if the amplitude of electric and magnetic fields are given. So as we know, electric field is the velocity of light in that medium times the magnetic field. So velocity is V0 by V0, which is 2.4 10 to the 2 by 4 into 10 to the minus 3. So this is 0.6 into 10 to the power 5 meter per second, but the official answer key says it is 0.5 into 10 to the power minus 5 meter per second. So this is not true because this is a very small velocity. So I think the right answer is this, but I don't think this is going to be the right answer because of its smallness. Okay. For 20th problem, identify the correct logic operation performed by the above circuit consisting NOR gates. So we'll consider the circuit from here. Now this is a NOR gate, so the output is A bar or B bar whole bar using the De Morgan's theorem. This is equivalent to A bar bar dot B bar bar, that is A and B. So this operation is essentially AND operation. Option C. A non-conducting sphere of radius 5 cm has its center at the origin O of coordinate system as shown in the figure. It has two spherical cavities of radius 1 cm, whose centers are at 0,3 and 0,-3 cm respectively, and the solid material of the sphere has uniform positive charge density 1 by pi microcoulomb per meter cube volume. Compute the electric potential at the point P, which is 4 cm, 0. So this is the configuration. Now the potential at point P is the potential of the full sphere minus this. Due to the superposition principle, the potential at the point P can be thought of first that there is no cavity in the sphere, and you need to find out the potential at 4 cm distance from the origin, and then you consider, instead of cavity, you consider two spheres in the positions of cavity with the same charge density of the solid material of this sphere, and then you find the potential due to these two spheres at point P. Then you subtract them and you will get the net potential at point P. Okay, now the potential for this, let's denote this by full sphere, and that is 1 by 4 pi epsilon naught. We have to use the formula for potential inside the sphere at a distance r. So 1 by 4 pi epsilon into q divided by 2 times r into 3 minus r square by r square, where r is 5 cm, small r is 4 cm, q is 4/3 pi r cube into rho, and the v, let's denote the potential due to this two sphere is Vc, which is 1 by 4 pi epsilon naught q prime divided by this distance. So if this is 4 cm, this is 3 cm, so this distance is 5 cm. This is q prime by 5 cm. So the net potential at P would be V full minus twice Vc, and if you calculate, you will get option A. This is a lengthy problem. Now question 30 says a very small sphere of mass 60 gram having a charge q is held at a height 7 meter vertically above the center of a fixed conducting sphere of radius 1 meter carrying an equal charge q. When released, it falls until it is repelled back just before it comes in contact with the sphere as shown in the given figure. Find the charge. So let's consider this as the level of potential energy. The gravitational potential energy is 0 here. Let's denote it by let's denote it by V is 0. So initially the total energy of the charge plus Q is, it has no kinetic energy, it has only potential energy, which is mg times this distance is 7 plus 1 by 4 pi epsilon, the potential due to electrostatic force, which is Q square by 7, and when it touches here, then also it does not have any kinetic energy, it has potential energy mg into 1 plus 1 by 4 pi epsilon naught Q square by 1, because this distance is 1 meter. Now using the energy conservation rule, you will get 7 mg plus 1 by 4 pi epsilon naught Q square by 7 must be equal to mg plus 1 by 4 pi epsilon naught Q square, and if you simplify, you will have 6 mg each 6 by 7 Q square by 4 pi epsilon naught, and you find out Q as 7 mg by 4 pi epsilon naught square root, and unfortunately by plugging in these values I am not able to get option B as answer. So if you can derive this, please write it in the comment. 31st problem says a tank with a square base of area 1 meter square is divided by a vertical partition in the middle. The bottom of the partition has a small hinged door of 10 cm square. The tank is filled with water in one compartment and acid, which has a relative density 1.7 in the other component, both to the height of 3 meters. Calculate the force necessary to keep the door closed. Let's draw the scenario first. Suppose you have a square box like this, and this is your partition. Here is your water, here is your acid, and here you have a door. Now the water and acid have different densities, so if you consider 2 points at the same level, then the pressure would be different for water and acid. Using the Bernoulli's formula, P water plus rho water times G into H must be equal to P acid plus rho acid G into H. Now P water minus PA is GH PA minus P water. Now this is 9.8 into 3 into 1.7 minus 1 into 1000, and the force that is acting on the door because of the pressure difference is delta P into 10 centimeters square, that is 9.8 into 3 into 0.7 into 10 to the 3 into 10 into 10 to the minus 4, and it would be 20.5 Newton, option C. What is the largest average velocity of blood flow in an artery of radius 4 into 10 to the power 3 meter if the flow must remain laminar? Also determine the corresponding flow rate. So as we know, the Reynolds number is the density of the fluid times the velocity times the diameter divided by viscosity. So for laminar flow, Reynolds number is 2000, and we'll use the CGS unit everywhere. So rho for blood is 1.06 gram per cubic centimeter. So you can write it as 1.06 into V into diameter is this is given in meter, so you have to convert in centimeter by multiplying 100. So this is 0.4 into 2 because we need to have diameter, divided by 2.084 into 10 to the power minus 3, which is in Pascal second. To convert it into poise, you need to multiply a factor of 10, and if you find out V, you will get 0.49 meter per second. So here, from here you will get V as 490 centimeter per second, then you have to convert it in the meter per second. And the flow rate is the volume that is flowing in 1 second, which is pi into the radius square times the velocity. So this is pi into 4 into 10 to the power minus 3 whole square into 0.49, and that is basically 2.46 into 10 to the power minus 5 meter cube per second. Option B is the correct answer. Thank you.